Optical mineralogy is the study of minerals and rocks by examining the way they interact with light. Most commonly, this means preparing thin sections, which are very thin slices of rock glued to a glass slide. We look at thin sections using a special microscope called a petrographic microscope. As an introduction to optical mineralogy, this video starts first with rocks in outcrop and in fist-side rock specimens. And then we show how to make them into thin sections. And we finish the video by discussing how we examine those thin sections using a petrographic microscope. However, we leave the details of optical theory and of thin section examination for another time. Petrologists start most projects by studying rocks in outcrop. This view shows an outcrop of the Duluth Gabbro in Minnesota. By studying it closely, perhaps using a hand lens, a geologist could identify white plagioclase and brown pyroxene in this outcrop. There's a limit, however, to how much information can be gained this way. For closer looks at rocks, petrologists usually collect fist-size hand specimens. Here are 4 examples. To get hand specimens, we generally knock large chunks of rock off the corners of outcrops. One great result is that fresh rock surfaces are now exposed, so the effects of weathering are eliminated. Sample number 1 is an altered metamorphosed basalt. Sample number 2 is a metapelite, which means it's a metamorphosed shale. It contains red garnets that are quite easily seen. Sample number 3 is a different metapelite. It contains red garnets, but also perhaps long needles of grains of a mineral called selenite. And sample number 4 is a blue schist from the Greek island of Syros. This rock too contains conspicuous garnets. To examine finer details in a hand specimen, we may use a hand lens. But even a hand lens cannot reveal everything that we want to see. Sometimes mineral identification is ambiguous. Often mineral grains are too small to see and identify in hand specimen. And many important rock textures are really microscopic, so we can't see them at all using this approach. This is why petrologists routinely make thin sections. The process for making thin sections is pretty straightforward. We start with a large piece of rock and cut it to smaller sizes, perhaps using a large rock saw like you see on the left or a smaller one like the one on the right. The goal is to create a slab of rock, which we can then cut into smaller pieces. So here's a rock partially on its way to being made into a slab. And ultimately, we create shoebox-shaped pieces called billets. The next step is to polish one side of the billet and then glue it to a glass slide. We cut the billet so it's just a little bit smaller than the slide. And then we use a special epoxy to fix the two together. Most petrographic slides are about 1 inch by 2 inches, which is smaller than the standard ones that biologists might use. We then use special thin section equipment to cut off as much of the billet as possible. We do this using the saw on the left side of this device. And then we grind to make the sample thinner. There's a grinding wheel on the right side of the device. The ultimate goal is to have a sample of uniform thickness equal to 0.03 millimeters. This is 30 microns, which is very thin. And here are some sample thin sections. Notice that these samples here have been polished. They reflect ceiling lights as bright flashes in several places. But sometimes, instead of polishing thin sections, we glue a cover slip to the top of them instead. And the glue between the cover slip and the rock slice fills any cracks or pits that might be present. Here's a slightly closer view of 2 of the sections we just saw. The rock on the right, the brown material, is biotite mica. The light-colored material is mostly quartz and feldspar. The rock on the left has much lesser amounts of brown biotite, but they're still a little bit present, and there are a few round obvious garnets. Once we have a thin section, we can examine it using a petrographic microscope, like the ones you see here. A key that sets this kind of microscope apart from other microscopes is that there are filters and a diaphragm in the substage that ensure that polarized light passes up and through the sample. And up near the top of the microscope, there's another polarizing filter that we can insert or remove if we wish. So we examine thin sections in two fundamental modes, with this upper polarizer inserted or with the upper polarizer not inserted. When we have the upper polarizer inserted, we see a sample in cross-polarized light. And when the upper polarizer is removed, we're seeing a sample in plane polarized light. Here is a view of a thin section in plane polarized light. The brown material is biotite in various shades of brown that change if we rotate the stage, and the green material is mostly hornblende. The opaque material, the black grains, are primarily magnetite. And the clear grains could be feldspars or quartz. In this view, identifying the biotite and the hornblende is straightforward, even if we might not have been able to see them in hand specimen. We cannot, however, identify the clear mineral grains with any certainty. Now we can stick in the upper polarizer to look at the same thin section in cross-polarized light. The colors we see are called interference colors, and they rarely match the color of the mineral grain in plane polarized light. The hornblende grains show bright pastel colors in blues and greens and violet. This is typical for hornblende. These are called high-order interference colors. The biotite here still appears a bit brown, but if you look, you'll see there's bright pastels on top of the brown. The grains that were clear in plane polarized light now show white to gray to black interference colors. Some of them show stripes, which are twinning, which tells us they are plagioclase feldspar. And other grains show what is called undulatory extinction. They go black at different times in different parts of the grain, which means they are quartz. So by examining this thin section in both plane polarized and cross-polarized light, we can identify all the minerals that are present, even if the grains are so small that we couldn't see them in hand specimen or with a hand lens. We have only looked at two of the standard ways that an optical microscope can be used. For making some advanced measurements, or in cases where other things are ambiguous, there are a number of other lenses and filters that we can insert as needed, and we will get a number of different views, which also will provide us with very valuable information. We saw these four samples before. If we want to know what the alteration products are in the altered basalt, we need to make a thin section. If we want to know what the different minerals are in the two P-light samples, we need to make a thin section. And if we want to know exactly what's in the blue schist from Greece, we make a thin section. Yes, we can see some minerals in hand specimen, but to really know what is there, we need a microscope.